Hello everyone and welcome. This presentation covers a 10-cycle inquiry for IPI 496, and it explores a really fascinating question: how can the mistakes that we've made in studying animal intelligence on Earth help us build smarter, less biased AI for exploring space? Essentially, if our methods for recognizing intelligence right here have been flawed, how can we avoid projecting those same flawed assumptions onto the cosmos? This presentation is interactive, and I'll share a link so that you can explore the data and sources in more detail. For now, let's dive into the journey. Cycle 1, the problem of measurement. So where does this all start? It starts with a fundamental problem: measurement. For decades, our tests for animal intelligence were deeply flawed. We were essentially giving animals human-centric puzzles and then acting surprised whenever they didn't perform as expected. We failed to account for the non-cognitive factors like motivation, personality, or simple physical differences. This created a direct parallel for AI. If we build an Earth-centric AI, it might look at the universe and completely miss truly alien phenomenon simply because it doesn't fit into our neat, predefined boxes. Cycle 2, ecological validity. Cycle 2 deepened this idea. It's not just that our tests were wrong, our entire approach was. We were testing intelligence in sterile labs, completely removed from the complex, messy reality where that intelligence actually evolved. The key insight here is experience-specific cognition. Intelligence isn't a single fixed score, it's a dynamic adaptation to a specific environment. For our AI, this is a game changer. It means the AI cannot just look for a signal in isolation, it must be able to understand the signal within its unique, potentially alien, ecological context. Cycle 3, human bias in AI. Of course, these flawed frameworks don't come from nowhere. In Cycle 3, we found that the biases in our AI systems are direct reflections of the biases in our own minds. Cognitive shortcuts and patterns from human psychology, like confirmation bias, are being coded directly into our machines. We see this with real-world consequences, like facial recognition struggling with minority faces because it was trained on biased data. The takeaway is stark. To build less biased AI, we first have to recognize and correct our own inherent biases. Cycle 4, a unified theory. This led to a crucial question: is there a single theory that explains why bias is so universal? Cycle 4 found one in the free energy principle. In simple terms, it proposes that any intelligent system, biological or artificial, must constantly try to minimize surprise. It does this by building an internal model of the world to predict what's coming next. But that very act of building a predictive model creates bias. This reframes the entire problem. Bias isn't a bug to be squashed, it's a fundamental feature of intelligence that has to be actively managed. Cycle 5, experimental validation. Now, that sounds very theoretical, but in Cycle 5 we found incredible experimental proof. Scientists were able to take living rat neurons in a dish and, using the free energy principle, predict with over 80% accuracy how they would self-organize and learn to process signals. This was a huge leap. It took the FEP from a grand theory into a practical, validated engineering principle, giving us a tangible roadmap for building bias-aware AI. Cycle 6, an architecture for active inference. So, if the free energy principle is the why, then active inference is the how. In Cycle 6, we found a concrete architectural blueprint for a robot that operates on these principles. The agent can navigate a completely new environment without any pre-training. Crucially, it uses its understanding of uncertainty to decide when to explore the unknown versus when to exploit a promising lead. It's a system designed for curiosity and adaptation, which is exactly what you need whenever you're looking for something truly novel. Cycle 7, the BLC1 case study. Next, we put these ideas to the test with a real-world case study. The BLC1 signal. This was a radio signal detected from the direction of our nearest star, and for a moment, it looked like a potential techno-signature. But a rigorous verification framework revealed the truth. It wasn't alien, It was a complex ghost signal created by our own Earth-based radio interference. The critical lesson was what we call the postage stamp problem. Analyzing a signal in isolation without its broader context can be dangerously misleading. This case gave us a concrete checklist for telling a true anomaly from a sophisticated fake. Cycle 8 provided the mathematical machinery for an AI to perform that kind of verification. A Bayesian framework called BADAC allows an agent to treat all data not as hard facts, but as fuzzy, uncertain probabilities. This allows it to distinguish between a novelty, something that's just an outlier to its current model, and a true anomaly, which is a signal that's inconsistent with any plausible natural explanation. It's the math of scientific skepticism. Cycle 9, the scatter problem. But even with this powerful math, Cycle 9 uncovered a deeper, more profound problem. In cosmology, a model named Steve revealed a hidden trap of circular logic. The model's ability to measure the universe was being biased by its own unprovable assumptions about how the universe works. It was stuck in a feedback loop. This is the exact problem from Cycle 1, but now at a massive cosmological scale. It proves that an AI can't just have a good model of the universe, it must also have a model of its own limitations. Cycle 10, conformal prediction and humility. This brings us to our final cycle and the keystone solution, conformal prediction. This is a brilliant statistical method that acts as a wrapper around any AI model, no matter how flawed. Instead of letting a biased model give you a confident but wrong answer, conformal prediction forces it to be honest. When the underlying model is struggling or biased, it doesn't fail silently. It produces a larger set of possible answers. It basically says, I'm not sure, it could be any of these things. This provides a mathematically guaranteed measure of uncertainty. It gives the system what we call epistemic humility. Conclusion and reflection. So to bring it all together, we started with bias tests that masked animal intelligence. We discovered that this bias is a fundamental part of how any intelligent system works. We found an architecture that allows an agent to navigate uncertainty and a real-world case that shows us the dangers of ignoring it. And finally, we found a mathematical framework, conformal prediction, that allows a system to quantify its own ignorance and act on it. This is the architecture of epistemic humility. It's about building AI that doesn't just give us answers, but tells us how much we should trust those answers. Reflecting on this process, I feel that this was an incredibly powerful inquiry. It wasn't just about AI in space, it was about connecting psychology, data science, and even philosophy to understand the limitations of intelligence itself. The biggest success was seeing how these different domains all pointed towards the same conclusion about managing bias and unknown unknowns. The main challenge, of course, was managing that breadth, keeping a clear logical story going while pulling from so many different fields. Ultimately, by embracing uncertainty, we can design systems that are not only more powerful, but also fundamentally more honest, and far less likely to repeat the mistakes of the past. Thank you, and please feel free to explore the full presentation at the link provided below.